Thank you so much for joining us this afternoon. It's a really exciting turnout for a panel that we're really excited about. I'm Keats Webb. I'm an imaging scientist at the Museum Conservation Institute. I want to thank the sponsors for today's session, that is Bruker and GC Laser Systems. We really appreciate their help in making this happen. We're not going to do a full land acknowledgement. I want to point to the land acknowledgement from the opening session, and then also the water acknowledgement this morning. And borrowing from the 2021 Museums and Race Virtual Conference, I want to encourage everyone to reflect on the history, stolen legacies, intentional oppression of whole groups of people, social circumstances, and personal experiences that bring us to this moment. We encourage you to think about whose ancestral lands you are on and what brings you to this moment. So this lunch session is designed to delve into the fundamental aspects of multiband, multispectral, and hyperspectral imaging in a welcoming setting that invites learning, inquiry, and exchange. The first part of the session will focus on light-matter interaction, focusing on the phenomena that provides the foundation for multiband, multispectral, and hyperspectral imaging. This invited presentation will be given by Kate Dooely, imaging scientist at the National Gallery of Art in Washington, D.C. The second part of the session shifts from the phenomena to the technique and will include two invited presenters to cover multiband imaging and imaging spectroscopy. Jiuan Chen, associate professor at Buffalo State University, will be presenting on multiband imaging, and Olivia Kuzio, assistant scientist at the Getty Conservation Institute, will be covering imaging spectroscopy, which include multispectral and hyperspectral imaging. Due to time, we're going to do questions at the very end of the session, so we'll go through the presentations and then take questions then. This session is a collaboration of the Book and Paper Specialty Group, the Photographic Materials Group, and the Research and Technical Studies Specialty Group, and the Imaging Working Group, lots of groups. The lunch session fits into a larger imaging program at the annual meeting this year, and that includes the joint specialty session looking at case studies of applications and interpretation, and a concurrent general session pulling together a range of media, techniques, and applications. So the lunch is being held at the beginning of the conference to lay foundation for the joint and concurrent general sessions. There will also be an imaging working group happy hour this evening, so if you're interested in attending that, please come find someone from the imaging working group. So as the briefest of overviews, the imaging working group is an international community of people, conservators, photographers, scientists, and more, interested in conservation and cultural heritage imaging. We prioritize communication, connection, and cross-disciplinary collaboration to develop and share resources, projects, and solutions. Our working group is hosted by the Research and Technical Studies Specialty Group. We have virtual quarterly meetings, monthly informal gatherings that range from guest presentations on imaging-related topics, virtual social events to connect the community, and lightning presentations for members to share projects and tips. In addition to building an imaging community, we also have been working on the Imaging Wiki, which is on the AIC Wiki platform. And this offers resources for community and will serve as an available knowledge repository and platform for resource distribution. Since this session is focusing on fundamental aspects of multiband, multispectral, and hyperspectral imaging that is encouraging this learning, inquiry, and exchange, we want you to walk away from this with some resources to continue to explore what you hear about today. So you can use the QR code here, but it's also on the online community, available on the online community, so you can access that document there. So at this point, I'm going to hand it over to Kate Dooely for the first presentation.
So today I will introduce some terminology you may encounter if you're doing spectral imaging, describe light interaction within a paint layer, including reflection and luminescence, and then introduce similarities and differences between multiband, multispectral, and hyperspectral imaging. So this is the electromagnetic spectrum, and it shows that the relationship between energy and wavelength is inversely proportional. So as energy increases, the wavelength decreases. So wavelength is denoted with this Greek symbol lambda, and it's defined as the distance between successive crests or troughs of a wave. And spectral regions, they are just different energy ranges within the electromagnetic spectrum. So your X-ray region is more energetic than the ultraviolet, than the visible, than the infrared, for example. So today we're going to be focusing on the ultraviolet, the visible, and the infrared spectral region. And in those regions, the wavelength unit that's commonly used is nanometer. And so for reference, 1,000 nanometers is equivalent to 1 micrometer, and a diameter of a human hair is on the order of 100 micrometers. So a nanometer is a really small unit of length. Now, some disciplines define the near-infrared spectral region as 750 to 1,000 nanometers, and then the shortwave infrared or SWIR spectral region as 1,000 to 2,500 nanometers. So today, all three of us presenters will try to use this near IR and SWIR terminology. And then finally, a spectral band. That is just the wavelength range that you're using to acquire an image. And then if you're not familiar with the term spectroscopy, it is a general term that refers to analyzing how a material interacts with light or other forms of electromagnetic radiation. So there's many different types of spectroscopy depending on what spectral region you're working in. So today we're just going to be focusing on spectroscopic techniques that involve diffuse reflection and luminescence. So reflectance is the amount of radiant energy, what we refer to as light, that is reflected from material relative to the incident radiant energy. And so the values range between 0 and 1. And so that's the formal definition. However, when we're working in a studio or a lab, we're really taking a relative measurement using a reflectance standard and then measuring the apparent reflectance. So this white tablet you see in this photo, that's a 99% reflectance standard across the spectral range that we're working over. So here we've got two light sources on either side of our detector. The lights, they're tungsten halogen lights that you typically find in a photography studio. And so what we measure then is light that is reflected off the artwork versus what is reflected off of this 99% reflector. So here's a diagram of a paint cross-section. Now these blue circles, these represent pigment particles that are suspended within a binding medium. And so you've got a paint layer here that's sitting on top of a ground or a preparatory layer. You might have a drawing line that is below the paint surface. And so you can have a couple of types of reflection as light interacts with your paint layer. So specular reflection then is when light is reflected off of a surface at the same angle as your angle of incidence. And so specular reflection, that's what you get if light is reflecting off a material like a mirror or a piece of glass. It's more pronounced on surfaces that have a high gloss. And then you can also get specular reflection off of a varnish. And so specular reflection does not contain any information about color or the chemical composition of your paint layer. Okay, so in contrast then, diffuse reflection, it's another type of interaction, but it can give you information about color and the chemical composition of your paint. So in this case, you've got light, it's incident on your surface, and it can get reflected off your surface at various angles that I'm not showing you in this little diagram here. But really what we're talking about with diffuse reflection is that most of the diffusely reflected light will have interacted with some volume of your paint sample. So you can have some light that gets absorbed by your pigment particles or other materials in your paint layer. Some light can get scattered by the particles at various angles. So in general, these bluer or shorter wavelengths, they're more likely to get scattered or absorbed, and they generally only interact with paint that's closer to your surface. And the redder or longer wavelengths, they're absorbed less, they're scattered less. So that means that they can penetrate farther below the surface. So they may eventually reflect off of the ground layer and then back out through the surface where we can detect them. If they encounter a drawing line that absorbs some of the light, then less light would get reflected in that area. So ultimately what we detect is light that gets reflected or backscattered through the surface. And because most of the light that we're collecting has interacted with some volume of your paint layer, it's encoding information about the absorption and the scattering properties of your layer. And thus, that's how you get information about the color and the chemical composition. So most objects exhibit a combination of both specular and diffuse reflection. So as I've mentioned, with diffuse reflectance spectroscopy, you are studying light that is reflected or backscattered from materials as a function of wavelength. And most of the diffusely reflected light that we detect has interacted with some volume of your paint layer or layers. So diffusely reflected light, that's what you're measuring if you're performing reflectance spectroscopy, like if you use a fiber optic reflectance spectroscopy instrument or FORS. Diffusely reflected light, that's also what you're measuring if you're doing reflectance imaging, whether that's multiband, multispectral, or hyperspectral reflectance imaging. So here on this plot, I'm showing you 4 reflectance spectra of different blue pigments in the visible spectral region. So the word spectrum, that is singular. So one of these curves is a spectrum. And the word spectra is plural. So here I'm showing you 4 spectra on this plot. And so as you move into the near-infrared and SWIR spectral regions, you've got more discriminating power among materials. So there are advantages for working over a wider spectral range. So here I'm showing you 4 diffuse reflectance spectra. So just to orient yourself to this plot, your y-axis, that is showing you the reflected light intensity. So you've got values here between 0 and 1. X-axis is wavelength. And so wherever you see like a dip in this curve, that's where you have a lower amount of reflected light intensity. And an alternative way to think about that is that that's where you have absorption of the light. So all of these little dips, these are just various absorption features. And so absorption features in the visible spectral region, they're usually due to electronic transitions that give rise to color. And absorption features that you see in the near-infrared and SWIR, they generally relate to vibrational transitions, which means like the stretching or bending of chemical bonds. And so that often relates, a lot of the absorption features in the near-infrared and SWIR often relate to like organic content from your binding medium. Not all, but a lot of them do. So the curve or spectrum you see here at the bottom, this is from a carbon black paint. So the pigment carbon black, that absorbs equally at all wavelengths. So it's got a low reflectance across the visible, the near-infrared, and the SWIR spectral region. So I'm showing you some of these spectra because the spectral features you see here, they relate to how these materials would appear in a reflected light image. So in a reflected light image, they're grayscale images. So your darker areas reflect less light than your brighter areas. So in the case where I've got carbon black, it's going to appear dark, no matter like what spectral region I'm looking over. It would show up dark in a grayscale reflectance image. Now, this dashed curve you see here, this is has vermilion pigment in it. So if, for example, you did reflected light imaging from 400 to 600 nanometers, where the vermilion is absorbing, vermilion would appear dark in that spectral region. However, say you image from 800 to 1000 nanometers, your vermilion containing paint is going to appear much brighter. So light scattering, that also can influence the intensity of your reflected light. So this uppermost spectrum here, this is a lead white containing paint. And so in the visible and the near-infrared region, it's really not absorbing light, but it is scattering light. So lead white's going to appear brighter in a reflectance image. So the next few slides just discuss working in the near-infrared and SWIR spectral regions in order to visualize features that are below your paint surface. And so on this slide, this is just a real-world example of this. This is a view from the Getty Museum Painting Conservation Studio when you're working in the visible spectral region. So you kind of see like the haze and the smog surrounding Los Angeles. Now, if you work in the SWIR spectral region, you can see you have less scattering and absorption by particles in the atmosphere. So you can see these San Gabriel Mountains in the distance. So this is really analogous to what's happening in a paint layer where you have less absorption and less scattering by particles within your paint. So generally you can penetrate and see, farther in the distance or farther below the surface. Okay, so these are several test panels that were made at the gallery to study the wavelength dependence to determine if you could visualize different drawing materials below paint that was made with different pigments. So we're just going to focus on one of these test panels today. So specifically, this is an example of trying to visualize a carbon black line below Prussian blue paint. So here I'm showing you some FORS measurements and then the reflectance spectra of a carbon black line. That's the curve here in black. And then also just the chalk ground layer, which is in yellow here. So we ended up taking FORS reflectance spectra of the Prussian blue paint that was only over the chalk ground. Okay, and so that spectrum is shown in this brighter blue color here. And then next we took a measurement through the Prussian blue paint that was sitting on top of this carbon black drawing line. And so that's what's shown in this darker blue spectrum here. So basically, in order to be able to visualize that black drawing line through the Prussian blue paint, you need to have a difference in the reflected light intensity, or this delta, this change in reflectance, compared to when you're on the black line to when you're not on the black line. Okay, so these are three reflectance images collected in different spectral bands. And in these spectral regions, there is no difference or change in reflectance. So I cannot see through the Prussian blue paint. However, as you start to have a difference in the reflected light intensity, you get this contrast difference, and then you can actually start seeing through the Prussian blue paint. So in this specific example, the spectral range between 1500 nanometers and 2250 nanometers, that's what's going to give us the best contrast of visualizing that carbon black line sitting on a white ground through the Prussian blue paint. So does it work in practice? This is an example. This is a Picasso painting from the Phillips collection, and there's a lot of Prussian blue paint used in the surface composition. And so with a reflectance spectral band image that's collected from 1100 to 1400 nanometers, we don't see much of the hidden portrait of the man below the surface because the Prussian blue paint is still absorbing in that region. However, if you move farther into the SWIR from 1500 to 1700 nanometers, you can clearly see this portrait of the man that's below the surface. So this is just a single example. Really, the optimal spectral band for visualizing subsurface features, it depends on several things, including the paint composition, the paint composition of the overlying layers, really, the thickness of those layers, the composition of your ground layer, and then like whatever subsurface material that you're trying to visualize. So there's not just a single spectral band that's going to work for every single situation. You kind of have to figure it out on a case-by-case basis. So these next slides, they discuss reflectance imaging. So the setup shown here, this is a multispectral setup where here is our sensor, which in this case happens to be a silicon CCD. Then you've got an imaging lens, and this is a filter wheel that has various filters in it. And so these filters, they allow us to collect images in different spectral bands. Okay, so here is the reflectance image where your spectral band is centered at 400 nanometers. Here's the spectral band image centered at 450. And this was using a set of filters that the spectral bands were centered every 50 nanometers. So you can see that the reflected light intensity is varying in these different spectral bands. So what you end up with then is this three-dimensional data set. So you've got two spatial dimensions, your X and Y, and then your third dimension is just this stack of images where each image is centered at different wavelengths or in different spectral bands. So wavelength, this is our third dimension. So we end up with this image cube, this three-dimensional image cube. Now, what I've circled here in pink, these are reflectance standards. So the thing that looks black, that's a 2% reflectance standard, and then the white one is a 99% reflectance standard. So if you include some reflectance standards in your scene, what that allows you to do is convert digital counts, that is the digital counts that are registered by your sensor, into reflectance. And you may want to do that because the detector is not equally sensitive at all wavelengths. Each filter can have different transmission properties. And so what that means, for the same reflected light intensity, you might register a different number of digital counts. However, if you've captured reflectance standards in your scene, you can correct for that, because you now know if you're looking at your white reflectance standard, it's a 99% reflector, and then your black's a 2% reflector, so you can correct for that and calibrate your images to reflectance. Okay, so that kind of just shows that here you might have a different number of counts off your white standard, even though you're still looking at a 99% reflector. But once you do that calibration to reflectance, you can correct for that. Now, if the calibration to reflectance is not done, that is multiband imaging. So multiband images, they are not spectrally calibrated. And so it's harder to compare intensities across different images in a multiband setup. Now, if you do calibrate to reflectance, then you can compare the reflected light intensity across all your spectral band images. So for a given pixel here in our blue leaf, right up top, I'm looking at this pixel here that's shown in pink. So for a given pixel in this blue leaf, we can plot the intensity at that pixel in all of our spectral band images. So what I'm showing you here, this yellow rectangle, this represents the wavelength range of that particular, of our first spectral band image. So this filter happens to be passing 40 nanometers, and then all of our filters are centered every 50 nanometers. So this pink dot you see, that's representing the average reflected light intensity in this particular spectral band at this particular pixel. So you can look at how the reflected light intensity varies for all of your spectral band images, and then you can plot that. That is your reflectance spectrum. Okay, so where you have a lower amount of reflected light intensity, that's where your image looks dark. So in these three spectral band images here, that blue leaf looks darker, and then as the reflectance increases, you can see that pixel on the leaf looks brighter. So once you've calibrated to reflectance, you can look at the reflectance spectra for every pixel in your scene. And because this happens just to be a multispectral setup, it means you're collecting generally in a few to tens of spectral bands. The spectral band images are not continuous. You can see I've got some gaps between my spectral bands. And thus that makes your resulting reflectance spectrum, it's the series of line segments, so it kind of looks like connect the dots. But this particular spectrum, it still has enough information, that I can identify that this is ultramarine based on this intense absorption near 600 nanometers. So if you've calibrated using your reflectance standards, so you've got a reflectance spectrum in every pixel, you're doing reflectance imaging spectroscopy. And I like the term imaging spectroscopy because I feel it conveys the fact that you can exploit your data by looking at images, or you can look at spectra. So this is an example from just kind of a simple multispectral system where you can at least begin to, separate pigments and sometimes, identify them. So this is an example from an illuminated manuscript that's been cut from a book, and you can identify spectra in your scene, and then potentially you can use different algorithms that will query your cube and help you map and create maps that show areas that have similar reflectance spectra. And so from some of the spectra, you might be able to identify some of the pigments. Like I can say, this light blue one's got ultramarine from this intense absorption here. Some of these look like, hey, they look kind of like a red lake spectrum. I can't tell you what red lake it is, but you can at least start separating out materials and maybe identify some. But with a system like this, it can also help you determine what other analytical methods and where you might want to use those analytical methods to help you identify the pigments. So in this case, this is just a map of the blue and green pigments displayed. And so you could use other point-based reflectance measurements, like with a FORS instrument, or you could do an X-ray fluorescence measurement to get more info. So then we could identify, some of these pigments contain azurite, and then those also are pigment areas that have copper. And some of the other copper green areas also have lead and tin. And so then you can infer that lead, tin, yellow was added. Okay, so this is an example now with a hyperspectral reflectance imaging setup. And for that type of system, you need a little bit different equipment. So you need some kind of dispersive element that essentially functions like a prism, and it separates light into its component wavelengths. So you still end up with this three-dimensional image cube, your two spatial dimensions, and then your third dimension is wavelength. And you can do the same thing of looking at reflectance spectra. So you essentially drill through this image cube at a given pixel, and you can plot how the reflected light intensity varies with wavelength. In this case, our spectral bands are contiguous, so we don't have any gaps between our spectral bands, and we have a lot more spectral bands, so our spectrum essentially looks continuous. This technique, this is also known as reflectance imaging spectroscopy. And so really the distinction between multispectral and hyperspectral, it's kind of arbitrary. I wouldn't focus on it too much. If you've calibrated to reflectance and you're looking at your reflectance spectra, then you're doing reflectance imaging spectroscopy. Okay, so now we're switching gears a bit to talk about luminescence. So luminescence, that is the emission of light by a substance that has not been heated. So there's many different types of luminescence, which are shown on this plot here. You don't have to focus on this too much, because today we're really going to focus on photoluminescence. And most of the time, what you're doing is you're probably measuring fluorescence, but it's okay to call it luminescence because that's the overarching term. So molecular fluorescence, that is the absorption of light at shorter wavelengths, and then the subsequent emission of light at longer wavelengths. So this plot here, this is showing you the relationship between absorption and fluorescence emission. So this curve, this is your absorption spectrum, and it's also known as an excitation spectrum. It shows you the wavelengths of light that are getting absorbed. So this particular example, this is the absorption spectrum for Eocene lake pigment. which is a red pigment that Van Gogh is known to have used. So you can see here, it's maximally absorbing here around 500 nanometers or so. And so in the fluorescence emission spectrum, you can see the shift in the fluorescence emission. So this maximum emission is near about 550 nanometers. So in general, the emission spectrum, it's a mirror image of your absorption spectrum. So oftentimes, the name of the technique you're using, it contains what wavelength region you're exciting over, and then what wavelength region you're monitoring the emission over. So for example, if you excite in the ultraviolet and then you monitor the emission in the visible, that technique is known as ultraviolet-induced visible luminescence. And so there's an upcoming Conservation 360 series book on multiband imaging that kind of defines and gives names for some of these techniques. In general, it's always good practice to note the excitation wavelength and then the emission wavelength that you're going to use for your collection. So just like with reflectance, where you can scale the counts you measure to a known reflectance standard, you can do the same thing when you're measuring luminescence. So you can adjust the intensities in your spectral band images to match the known emission intensity of a standard. And so here is a target UV calibration target that you can use to scale the intensity of the luminescence. You could also use luminescent paints where you know their luminescent spectra. You just need to make sure that you're measuring your sample and your standard under the same conditions. So when you're doing luminescence imaging, it's a good idea to use non-fluorescent targets, a white target in your scene, to report on any light leakage. So these are our reflectance standards that you've seen before, and we include them in our scene because we want them to appear dark in our luminescence image. So if, for example, your white spectrum, your white standard appears some shade of gray or white, then it means that you've got signal contributing to your image that is not the luminescence that you're interested in. So including these standards in your scene, it's really just to report if you have any light leakage in your system that you need to track down and eliminate. So in this example, we were looking for luminescence from eosine lake pigments. So another thing to be aware of is that you might have some luminescence in your image that you collect that is not from your target of interest. So to help you out and to better identify materials, you can look at the luminescence spectra. So this yellow dashed line, this is where we started collecting the emission. And in our image, we can see that the most luminescence intensity that we see is in this white flower. But rather than having a shifted emission max like we'd expect for eosine lake, this white flower corresponds to this kind of green curve here. This white flower has an emission that just decreases from where we start collecting. So it's not consistent with eosine. So I can tell that by looking at the emission spectra. But I wouldn't necessarily know that from looking at the luminescence image alone. Now this slide shows the effect that non-luminescent pigments can have on your luminescence images and spectra that you collect. So this example, this is just a paint sample that's got vermilion and linseed oil. It's painted out on a glass slide. So here we've illuminated in the ultraviolet region, and then we captured the visible luminescence with a color camera. So this paint, it appears to have this kind of orange-red luminescence. But vermilion doesn't luminesce. So what's happening here is that the vermilion is absorbing the luminescence from the oil. So if you know what the reflectance spectrum of vermilion looks like, that can help you in the interpretation. So here, I mean, this is showing that vermilion is absorbing out to about 600 nanometers. It stops absorbing like when the reflectance increases. So here it's absorbing in this region the luminescence from the oil. It stops absorbing and hence has this kind of orange-red appearance in your luminescence image. So in this next example, this is a Van Gogh portrait from the Museum of Modern Art. Now this is a false color image. It's made from 3 spectral band images from our raw fluorescence cube. And it appears that you've got a lot of fluorescence, including in his jacket, which has this kind of reddish fluorescence. But I know from the reflectance spectra that this jacket's got ultramarine, because I can look at the reflectance spectrum and identify that. But I also know that ultramarine doesn't fluoresce. But because it's got this strong absorption near 600 nanometers, and then its increase in reflectance here, it ultimately results in kind of this pseudo-fluorescence peak in the fluorescence spectra. And so anyway, that absorption from the ultramarine makes it appear that you have this other like fluorescent component with an emission max near about 700 nanometers. So the absorption by other pigments, that can also influence your images and as well as your luminescence spectra. Now there is a way you can correct for that by using a procedure that uses your reflectance spectra and the spectrum of your excitation light. And so after you do that procedure, you end up with this corrected fluorescence image cube. And then you can look at the false color image made with the same 3 spectral bands. That looks different. Overall, there's less fluorescence or luminescence overall. And you can see that the emission spectrum from that same pixel in the jacket looks a lot different. Now, the image also indicates that you've got some strong signal occurring in the beard and the hair. So you can look at a luminescence spectrum from a pixel in the hair, and it shows that the luminescence spectra has got the correct shape for Eocene lake. Okay, and so then you could actually use some kind of algorithm to query your image cube, see where, like what other pixels have this type of spectrum, and then you can end up with a map for Eocene lake. So that kind of wraps up my portion of the talk. And then next up, Jiuan is going to talk about multiband imaging.
Thank you, Kate, for laying the foundation about light matter in action. And I'll follow that to talk about multiband imaging, basically just on photography side, not the spectra or spectrum or spectroscopy. Let me move this a little bit. So I'm going to focus on multiband imaging using modified UV with IR silicone-based camera, and which is an RGB, also called color cameras. And I walk through some common techniques, how they work, and what we can gain from the image captured. Silicone-based digital camera sensors, either CCD or CMOS, have a different spectral sensitivity than our eyes. To make them simulate human vision, manufacturers add some actual components to them. The native sensor cannot distinguish colors, thus tiny red, green, and blue filters are placed over individual photo sites to filter in only red, green, or blue light. From the red, green, and blue light collected to reconstruct the image in color. Here are 2 examples showing the spectral sensitivity of the CMOS sensors with their RGB filters. As you can see, the filters don't just pass visible light. They also pass through some UV and a lot of IR. To block that excess infrared and attenuate red filter sensitivity in order to make the camera better match human vision, an IR blocking filter is added on top of the sensor. So to modify a camera to capture UV, vis, IR, it is simply to remove the IR blocking filter. These bring back its full spectrum range from 350 to about 1050 nanometer, covering UVA on the shorter wavelength side and near IR on the longer wavelength side. This modification can be done through specialized photography shops, or you can buy modified cameras direct from them as well. And there are a lot of them now than 10 years ago. When considering a camera, we often want more resolution. Yes, that's great, but for me, the most critical feature is live view. A spatial live view, when tailored to a computer or tablet, since we cannot see UV or IR with our eyes, we need to rely on the camera to show us a live image to help us focus these wavelengths correctly. It's also key that camera supports raw image capture for consistent post-image processing. As full lenses, Abercrombie lenses are great because they can bring UVA, visible light, and near IR into focus on the same plane, making it much easier to capture images across wavelengths. But Abercrombie lenses are very expensive. Some are running more than $800 now. You can still use regular lenses, and you will need to refocus for each waveband. And this results in slight difference in the fields of view, which make image registration tricky. The great news, Grace Wilkins and I will be presenting a simple solution to this image registration problem tomorrow. It is a quick 10 minutes talk, so come by and check it out. Now with the spectral sensitivity expand from UVA to near IR, these modified cameras can still be used for all the common conservation imaging techniques that we use today. Even balance the normal illumination, raking, specular, transmit light, and visible luminescence that induced by either UVC or UVA. In addition, you can also do reflect near IR, transmitted near IR, visible induced IR luminescence, and reflected UV techniques, all with the same camera. All these images are taken through broadband filters to capture either UVA waveband, visible light waveband, or near IR waveband, hence multiband imaging. Because we cannot see UV and IR images are typically rendered in grayscale. And due to time constraint, I will not talk about raking or specular, and if you have a question, I'm more than happy to answer afterwards. One quick clarification, the so-called normal illumination is actually reflected visible light image. So to be consistent, I will refer it as reflect visible, just like a reflect UVA and reflect near IR. All these techniques fall into three categories of light matter interaction that Kate mentioned earlier: reflectance, transmission, and transmittance, and luminescence. Let's look at reflectance imaging first. This is about how materials absorb, reflect, or scatter light. It does not matter which waveband we use, the lighting is to be even or balanced. The example here shows the different degree of absorption of UVA or near IR by these watercolors here. Absorption means dark or darker in the resulting images. Reflected near IR can be very useful in seeing on a drawing or on a painting, as Kate mentioned, because some material become transparent to near IR, revealing what is underneath or beneath. As seen with these three lower these are lower watercolors over here. They become transparent in near IR, exposing the carbon black underlying drawings on lines. Same as this technique, as this example, the under drawing or under painting is fairly visible in the reflect near IR image because the paint cover is somehow transparent to near IR. Reflect UVA on the other side can emphasize surface texture because UVA has shorter wavelengths. It scatters more easily and highlights surface features. like the brush strokes seen here. I'm going to just showing the details so you can see the texture better. Because of that, silver mirroring showing up bright in reflect UVA image because the fine metallic silver on the surface is highly UV reflective. Now, what makes all these possible is proper lens filtration. And we pass the waveband we want to collect and block everything else. So for reflect UVA, the goal is to pass only UVA and block everything. For reflect visible, we need to block UV and IR and attenuate red filter sensitivity. For reflect near IR, we want to pass IR and block visible and UVA. And there are different IR passing filters as seen here. I have a list of different filters over there, such as Kodak Rentum 18A, 87, 87C, 87B, and 87A. And they each pass different IR wavelengths. I will explain more about this in a bit. So I have compiled a table with equivalent filters for each technique. It will be available in a Conservation 360 upcoming. Since filter block unwanted light, reflectance imaging can even be done outdoor. Sunlight has UV visible and IR wavebands. Okay, each IR filter starts passing light at a different point. So for example, the 87A began passing around 715 nanometer and reached 100% transmission around 780 nanometer. Kodak 87A, by contrast, starts around 880 nanometer and peak around 1100 nanometer. The longer the wavelength, the more transparent some material become. That is why, if I want to see on a drawing or on a painting or hidden features, I will often choose filters that like 87B or 87A to capture the longer IR wavelengths. Let's see the example here, the angle. These are the iron ink and then blister ink become more transparent as IR wavelength move to a longer side. Transmittance imaging is about light shining through an artifact. For these, the room needs to be dark, so only transmit light is recorded. It is great to study watermarks, paper fiber structure, cracks in the basket, or even stained glass, and more. The light setup for transmit IR is the same as transmit visible, but the light source needs to emit enough IR, and condenser lamps always are good options. Transmit IR can reveal features that reflect IR or transmit visible cannot. For instance, this image here shows a light post that's completely hidden in reflect visible light, but clearly visible in transmitted IR. The filters used for transmit visible and IR are the same as those used for reflect visible and reflect IR. I want to highlight a classical article by Dan Kuzio from 1985 that explains why transmit IR is often better than reflect IR for revealing under drawings. Here are two examples among many that I have encountered where transmit IR is more effective in revealing hidden features than reflect IR or transmit visible. Move on to luminescence. Luminescence imaging is about which waveband that you used for excitation and where the resulting luminescence appears in the spectrum. It is common to use UVA as excitation source to produce visible luminescence, or use visible light to excite and produce luminescence in the near IR range. For example, you can see different white media used in this drawing, and also where varnish is being removed and cleaned. And for this image that UVA was able to reveal the Iranian glass, and also in UVC to see maybe there's a lead containing glass in there. Okay. Right. So it is well known that pigments or dye like zinc white or rose madder will emit visible light when excited by UVA, while the cadmium-based pigments emits IR after excited by visible light. Egyptian blue is also known for its strong IR emission after exposed to visible light. The bioluminescence technique can be effective in revealing faded inks that are hard to see otherwise. Just like transmitted imaging, the environment needs to be free of wavelengths that you are trying to capture. For UV-induced visible luminescence, that means the room should be darkened with no visible light present. To get the strongest luminescence signal from the artifact, it is ideal to position the UV sources in an axial, like heads-on direction. Since you're trying to capture visible light here, it makes sense to use the same kind of filter used for reflective visible imaging, like sharp BG30A or X961 showing here. However, most UV sources do not just emit pure UV. They often emit some deep purple light, which cannot be completely blocked by the sharp BG30A alone. Traditionally, a Kodak 2E filter has been used to block UVA and visible light wavelength shorter than 420 nanometer. And it is still a great option for modified camera. And so the common filter combination is sharp BG30A paired with the Kodak 2E. In my experience, when using sharp BG30A, I have found that the BG30A or the Pekka 19 or X9 BP1, often used for standard cameras, may not be necessary. For bioluminescence technique, the environment needs to be free of any IR. The challenge is that most room light sources, even those that seem minimum, still emit some amount of IR. Because of these, the room usually need to be darkened and ensure clean image capture. Since this is a luminescence technique, the light source can be positioned in an axial position to deliver the strongest illumination directly onto the artifact. Because we capture IR, it makes sense to use the same set of filters as those used for reflected IR or transmitted IR techniques. However, since IR is invisible to human eye, and we often don't know exactly what IR wavelengths the material will emit, it is best to use a broader IR passing filter such as Kodak 88A that capture the widest range of possible emission. One of the biggest challenges, as actually Kate mentioned, is in luminescence imaging, is to make sure there is no overlap between the wavelengths coming from the exciting source and those emitted by the materials. In practice, this means that UVA lamps need proper filters to block any visible light from when doing UV-induced visible luminescence. And visible light source need to be IR-free as possible when doing visible-induced IR luminescence. So take UV-induced visible luminescence as an example. The GE black lights don't just emit UV. They also give off some purple, blue, red, and even IR. The UV system super bright UVC unit also emits a small amount of purple, deep purple. If any of these visible wavebands overlap with what we are trying to capture, that can cause noticeable color shifts in resulting images, as you can see here. You can see this clearly with the white standard actually Kate pointed out, placed along with my test sample. It picked up some purple and blue, which means that some of that visible light coming from the GE black light is being recorded in the resulting image. A simple and inexpensive way to check these is to use a stainless steel ball bearing, and which is highlighted in here. You can see the two light that reflect on the stainless steel ball bearing. So what has worked for me? I make sure that every UV lamp I use has a dark glass filter to block as much as visible light as possible. And I add IR blocking filters like sharp BG30A, which is my favorite filter. As I talk through the whole talk, you can hear me talk about BG30A. And over the visible light sources to block IR from the excitation source. Okay. For me, keeping the setup simple is key. It helps maintain consistency. So for example, I use a pair of visible lights that also emit IR. These can stay in the same position for both reflected, visible, and reflected IR techniques. Similarly, I place a pair of UV lamps in the same position for both UV-induced visible luminescence and reflect UV techniques. Visible induced IR luminescence, it is ideal to use a pair of visible light with proper IR blocking filter positioned axially. You can get away even just with one light for this technique if needed. When it comes to transmittance imaging, if you want to include transmitted near IR as a technique, make sure the light source emit enough IR. So halogen lamps are a good option for that. We can build as a light table or put the halogen light behind the object to capture the transmit IR. Filter choice can also be simplified. As shown here, I use the same X9 CC1 across several techniques. In the end, I only need around 6 filters to cover all the techniques I talked about. I would like to take a quick moment to talk about background materials. This is a quick test to show how the background can influence results. I place a paper fragment onto 2 different gray backgrounds. One is N5, which is neutral gray, middle gray, painted on a plastic sheet. The other is gray paper backdrop marked for photography. Under UVA, the paper gray background luminesces blue, while the N5 background does not. At first, I thought, it might be just a visual illusion. But once I cropped the background out, it becomes clear that the luminescence background alters the result. So my preferred background is something that appears middle gray for reflectance imaging and dark for luminescence imaging, as Kate pointed out. Okay, finally, I want to kind of circle back to the images themselves. With the modified UV-Vis IR camera, it is possible to carry out a number of imaging techniques using a single camera, and just by changing the light source and lens filter. So by examining this imagery, we can really learn a lot about the artifact. In addition, the RGB color images can be split into grayscale images. All these grayscale images can then stack together to build image cube with a free open source software, Spectral Analysis, and I would like to shout out to Dr. David Messenger and Dr. Decker and the Misha team at RIT to develop this fantastic tool, and I wish I known this earlier. With the image cube, you can actually combine any 3 grayscale images to generate 4 color composites, or run one of the 4 image analysis to further reveal features that might not be visible in the individual images alone. Do I have enough time? Okay, no, okay. I do have a video to show how they work, but I'm gonna skip that now and then maybe later. And just some of great resources that I often go back to. Sure, the upcoming volume of Conservation 360 is not there, but it's coming. And it's incredible resources for multiband imaging. And also, return to AIC's guide, particular chapter 6 about photographic techniques written by Dan Kuzio. Although it's written back in 2008, it's still very, very relevant and very clear and thorough research by Dan. And the user manual by a team at the British Museum is also great resources. Conservation 360 Volume 1 is about UV-Vis induced luminescence. It's wonderful. And there's a link to Misha if you want to know about Misha and download the software from there. Thank you.
Hey everyone, thanks for hanging in, catching this third part of our discussion here. So now we're going to switch focus to imaging spectroscopy. And I do feel really lucky to have the privilege of going last so that I can follow on Kate and Jiuan's presentations, because they already did so much of the heavy lifting here, right? They introduced a lot of topics that are going to be foundational to imaging spectroscopy, and you've made my job a lot easier. So thank you both for that. So using those foundations directly here, the first thing I want to do is to clarify how imaging spectroscopy is different from both conventional imaging here and then from the multiband techniques that Jiuan just talked about. Because I'm pretty sure that those two are the more familiar ones to this audience. So let's just start by taking a look at a regular off-the-shelf color camera. There's my laser pointer. It's a color camera because it has these 3 broadband color filters that are integrated with its sensor in that bare pattern, like you've already seen, which means that the light it captures is separated into 3 buckets, or these 3 bands based on its wavelength. And I call these broad bands because relative to band sizes that I'm going to show in a few slides, these are definitely broad. Each has sensitivity over maybe like 100 nanometers or more, like I'm showing here on this spectrum. So then if I swap out that regular off-the-shelf camera for one of these modified cameras that Jiuan talked about, it's had its internal IR filter removed, and then there's the option to collect radiation beyond the visible 400 to 700 using broadband filters with these specific cut-on and cut-off wavelengths to limit the radiation to other desired ranges. Again, exactly what you just heard. Jiuan described this so well and with so much more nuance than I've put here, but I want to create this visual, so of these broadband characteristics, and then moving forward, compare that to these much more narrow band sampling characteristics of just a generic imaging spectrometer. I'm probably going to use imaging spectrometer and spectral imaging system interchangeably, but what I mean by either of those is just an imaging system with many of these narrow band images that are being acquired. Hopefully, I've clearly illustrated that these narrower bands sample much smaller wavelength ranges than the broad bands of that conventional camera or the multiband system. And depending on how these narrow bands are created, more on that in a second, they might be on the order of like 40 to 50 nanometers wide, like here, down to even just maybe 2 or 3 nanometers wide for certain spectrometers. And this is where we arrive at what actually makes imaging spectroscopy different, which is the fact that with this narrowband segmentation, you've sampled the radiation at small enough increments to obtain spectra from the data. Kate, you illustrated this really beautifully earlier. Hopefully you'll recall that a reflectance spectrum, like I'm showing here, it shows the amount of radiation reflected with respect to wavelength. In a practical sense, again, it's that amount of digital signal collected in each of those narrow bands of the imaging spectrometer. And I'll just say that one nice thing about us scientists is that we can be really literal, and it works to our advantage here, right? So the name of the technique itself, imaging spectroscopy, implies exactly what it provides you with, both images and spectra. Okay, so one feature that tends to differentiate spectral imaging systems from each other is their spectral resolution, which is essentially the number of distinct bands that they're able to collect. A system with a higher spectral resolution than this one might measure this same spectrum like this, where in both cases we've obtained spectral data, but here with a slightly higher spectral resolution. And then thanks to these even narrower wavelength bands that sample that radiation in smaller chunks, we've just got more spectral detail here. Using a system that gets you this level of detail isn't always necessary, kind of depends on your needs and the questions at hand, but it can be useful to help you interpret the data for certain kinds of chemical investigations. The bottom line and the takeaway from this first bit, these first slides here, is just that imaging spectroscopy is what it provides by design, so images and spectra. Everyone loves a good origin story, right? So before we dive into the current state of imaging spectroscopy in our field, let's look back on where things began in the field of remote sensing. So folks have been strapping cameras to planes and stuff since like the mid-19th century, but it wasn't until the 1960s that the first imaging spectrometers were sent skyward to do things like land surveys. So folks were studying things like soil composition and vegetation health. And it was the evolution of these remote sensing instruments that eventually inspired the development of spectral imaging systems for pointing at paintings, basically, instead of the Earth. And the earliest of these was the Vasari project. Again, with these really literal names, this stands for the Visual Arts System for Archiving and Retrieval of Images, which was at the National Gallery, London, and you might find David Saunders wandering around the conference. I don't think he's here today, but this is some of David's work. So the goals for this system were to first capture imaging data that was useful for producing high-resolution color accurate documentation of paintings, and then also applying imaging processing methods to do things like discriminate between materials and probe for hidden details. If we fast forward 30 years later to present day, there has been an explosion of this kind of technology that we still point at art and that we continue to use to probe pretty much the same kinds of questions. So please note, on this slide, these are examples, not endorsements. Really, it was just my goal here to show a variety of systems in terms of context, complexity, cost, portability, all these things, which are some aspects that we can discuss more later if there's interest for each of these. But in the interest of time, I'm going to kind of go light on the details for any one and talk about some other stuff. So first things first, you'll probably notice I've sorted the systems into two rows based on whether they're typically called multispectral on the top row or hyperspectral, HSI, on the bottom row. The difference between these two categories is usually cited as the number of bands, that spectral resolution that they capture. It's not totally cut and dry where the line is drawn between the two, how many bands sort of take you into hyperspectral territory versus multispectral, and I just want to offer a slightly different perspective. So for those multispectral systems, the bands are typically created using narrowband filters or narrowband LEDs, where again, narrowband in this case means like on the order of tens of nanometers wide, right? So MSI systems are going to collect on the order of tens of these bands across the wavelength range of interest. For hyperspectral systems with even narrower narrowband sampling, remember we're talking about 2 or 3 nanometers wide now, creating bands that are this tightly sampled requires just different hardware entirely. They're going to rely on an internal dispersion element, like a diffraction grating, to separate out the incoming radiation into these really tiny segments. And this provides then usually on the order of hundreds of bands. So yeah, the number of bands you're able to collect with MSI versus HSI are definitely different, but the different band quantity is actually kind of a consequence of the actual hardware-based distinction between the two and how you're physically creating these bands, right? And I just want to say, at the end of the day, the distinction can maybe be a little arbitrary anyway, because if you're using your imaging system to measure spectra, you're doing imaging spectroscopy. Okay, so regardless of the system used to separate the radiation, you then need to detect it. Most folks, I think we've heard this a few times today, have heard of CCD and CMOS. So these are the silicon-based sensors that are in consumer cameras because they're sensitive and visible for color imaging, and also out into the near IR. So to call back to those example systems, I think the latest generation of that Megavision system uses cameras with CMOS sensors. Okay, so then spectrometers that are sensitive in the shortwave infrared, and beyond actually, have to employ sensors that have different properties to be sensitive over there. So they'll be made of different semiconducting materials like indium gallium arsenide, or InGaAs, you might have heard that, indium antimonide, or INSB, and mercury cadmium telluride, or MCT. And actually MCT, another reference point here, that's the kind of sensor in the head wall HSI system that was used in some of the night watch studies at Rijksmuseum. So takeaway here on this slide, just based on what sensor they employ, different systems are designed to probe different wavelength ranges. Why would you want to probe these different ranges? Kate spoke about this earlier, so different kinds of scattering occur when radiation interacts with a material, and these are recorded in the shape of the spectrum when that radiation is detected. These features, these absorptions, these reflections, these are what help us identify the materials that imparted them, because by nature they imply the presence of certain atoms and bonds, and they occur in really specific places in the spectrum. The features in the V-near are associated with the excitation of electrons, which provides information about color, and the features in the SWIR relate to chemical bond vibrations, bending, stretching, and these give us information about the molecular structure of materials. Kate also touched on this, and it's really important, so emphasizing it again. This flowchart comes from a really great JAIC publication from 2019. If you haven't noticed, I've been citing things in the bottom corner, all these publications to look at. It is a wonderful resource that discusses good practice for reflectance imaging spectroscopy setup and calibration procedures. I'm gonna send you there to that paper to follow up on the details of some of the other corrections that it outlines, but again, drawing your attention to this spectral calibration step. You've got to image and calibrate to a reflectance standard in imaging spectroscopy because, again, it's that step that transforms the captured data from raw digital signal into reflectance and helps you account for differences in your sensor, things like that. Often, that reflectance standard is one of these Spectralon pucks or tablets that you'll see. And yeah, really, really important to introduce that standardization. Okay, a few things about how this data is collected and structured. So because spectral imaging sets consist of a series of 2D images, an image for every band, the data set is a 3-dimensional thing called a data cube or an image cube. So in this figure, every single tiny, tiny cube represents a single pixel of the big, larger data cube. X and Y are the 2D axes of the image planes, and lambda is the orthogonal z-axis where wavelength is changing. So the two most common ways to collect data cubes are by wavelength scanning. So you're collecting 2D XY images of each band sequentially. This is the kind of strategy that you'd use Cultural Heritage Science open source. This is the system there. Narrow band filters are placed on the camera one at a time, and these bands are captured sequentially. Other systems are designed to collect image cubes in a line scanning fashion, where every waveband is collected one spatial line of pixels at a time. So this is how this surface optics hyperspectral system, Kate's system, works. An object is moved slowly, horizontally in front of the system, and the data cube is built up vertical line by vertical line. But either way, the resulting data is organized in the same way, right? Spatial XY images all stacked up according to wavelength. Structurally, this means that there are two ways to begin to interrogate a data cube. Because of the spectroscopy part, each pixel has a spectrum representing the interaction of light with the material at that location. And because of the imaging part, each image shows how the materials across the spatial composition interact with light relative to each other in that waveband. So for example, this pixel that I pulled out of the blue garment reflects slightly longer wavelengths, whoops, sorry, up here, between 550 and 650, but I'm saying it backwards. We're reflecting bluer wavelengths down here between 400 and 500. and absorbing between about 500 and 600. So if I pull out an image here from about 620 nanometers, it makes sense where we're absorbing a lot of the light, that blue garment appears dark relatively, right? So this is really powerful stuff. So for the final few minutes of my time up here, I am, drum roll please, gonna show some of the cool things that imaging spectroscopy can empower you to do. So this includes characterizing and mapping materials, revealing insights into object condition and history, and visualizing objects in new ways. So using these examples and probably not the extras because I don't think I have time. Okay. So first up, illustrating material mapping. Imaging spectroscopy of this Romano-Egyptian Fayum portrait from the 2nd century AD at the National Gallery. Here, it was used to characterize the painting materials and better understand the production methods that went into creating it. So you're looking at a color-coded classification map that indicates the distribution of spectrally similar pixels. And these are the corresponding spectra representative of these areas. So in some cases, these spectra represent a single material. So I believe for the red and the green spectra, these correlate with hematite and a copper-based green pigment. But there are other spectra here that are a little bit harder to untangle. So the purple up here and the pink, these were interpreted to account for mixtures of a red pigment and a white pigment, right? And it's a little bit harder sometimes to tease these things apart. So these classifications, looking here in the V-near area of the spectrum, all have to do with color. But then looking in the SWIR region, the absorption just above 2300 nanometers was used separately to identify the paint binding medium here as melted beeswax or encaustic. So using that signal then can map across the entire surface and map where that beeswax is present. So it's present everywhere except in areas of loss and areas where there's a highly absorbing black pigment where you can't really pull that signal then out of the data. Slightly different flavor of material mapping. Imaging spectroscopy was used in this case to deduce the presence of non-original material. So this is a detail from a late 13th century Sienese panel painting of the Madonna and Child with 4 angels. A broadband IR reflectogram was collected, covering 1,000 to 1,700 nanometers, and it shows similar gray levels across the entire face. This indicates that the average reflectance in that area then is pretty similar across that big wavelength range. So it's not until constructing a false color image from spectral images in this area that material differences became apparent. So here I've placed the 1650, 1400, and 1050 bands in the red, green, and blue channels. And this reveals that that area between the eyes is different from the rest of the face, right? A representative spectrum then from that area, this one, suggests the presence of the filler talc and indicates that, yeah, this was an area of past restoration. And then the black spectrum, in contrast, is consistent with the ground and pigmentation of the original composition. So a nice way to tease those two things apart. Another example, revealing the invisible. So the paper substrate for this study for Balthazar has writing on it. It's clearly visible in some areas, pointing out here, sort of on the tunic and the shoulders, but it's covered by thick paint layers in others, this thick white paint. We wanted to visualize the text here. We wanted to use spectral imaging, but it wasn't as straightforward as the last example, where just pulling bands out of the cube and putting them together helped reveal contrast. Here, instead, we had to turn to applying a mathematical transform. Jiuan alluded to these at the end of her talk. Here we used PCA, so principal component analysis. And this transform, it just gives us the ability to visualize variance in the data in a different way. So I'm showing you details from PC bands 9 and 10 here. And they've been reconstructed and they give us this new way to look at the data. And happily, in this case, it was a good result. So this helped us reveal the obscured writing under the opaque parts of the scarf really, really well. Very happy curators. So one thing to note here, these particular data were collected by us at the Getty with a hyperspectral system. We had 800 bands to play with here with the PCA. And the fact that we had that much data to throw math at, it definitely makes a difference. You might be able to pull out more discernible, more subtle details, than if you'd had fewer bands to work with. But I definitely want to be sure not to mislead or discount the power of lower band count systems for performing, very similar discovery or sort of revelation type tasks. So I'm showing here, this is a late 14th century manuscript and an 8th century parchment scroll that were both imaged with the Misha system. So Jiuan also called this one out. Misha produces 16 bands in the UV, Vis, and near IR. And then oftentimes they'll use statistical analyses to look at their data too. So PCA again proved super useful here to create contrast and revealed hidden details. So brought out text where it had faded that I've circled here. And on the parchment scroll helped really bring out these pictorial details. So details of a lion here, a serpent here, and some of these floral adornments that weren't really even visible in the visible image. Okay, wrapping things up. Just tying things together, thinking about where this all got started, 30 some years ago with that Vasari project, go bug David. Thinking about these questions of color accuracy, material discrimination, and revealing hidden details. The technologies that we use to probe these kinds of questions that remain pretty persistent in our field have come a long way, but I want to make sure to float the reminder that like any of the analytical tools that we use, imaging spectroscopy is a tool, right? It's not the tool, not the be-all, end-all. We don't work in a vacuum. We've got to continue to do complementary analyses. It's why we have Raman spectrometers. It's why we have FTIR. All these things to help get us to 100%, very confident answer. But definitely not ending on a discouraging note here. I'll just leave this example here, sort of looking to, new horizons. It's probably not surprising that folks are starting to throw artificial intelligence at these data cubes. There is so much data in an 800 band imaging spectroscopy data cube. Artificial intelligence can hopefully help us mine those a little better than we can do just by ourselves. So take a look again at that paper. We can talk more about it. There's a lot to talk about here. I'll say thank you.
All right, so we have some time for some questions. What I'm going to do is provide a few tasks for a couple of people. If the speakers can come back up here, if Adam can come up here and grab the microphone, and if all of y'all can start to think about your questions. I do want to acknowledge the contribution that these presenters have provided today. They are not presenting on their research. We asked them to present on these specific topics for all of you, and it took a lot of time and energy. So a big round of applause for these three. All right, and we'll open up the floor for questions.
Hi everybody, I have a very specific question, and I apologize in advance to everybody else. Oh, sorry. My name is Olivia. I'm a research fellow at the Textile Museum, and I was wondering if any of you had any insights as to differences in, again, very specific, differences in behavior between the same colored compound when used as a dye versus used as a lake pigment. I've been trying to adapt the VIVL technique that's used in paintings to textiles, and either I'm doing something very wrong or the behavior is very different between the two. So I was hoping to get some input on that.
Can you? Yes, okay. I don't have any specific experience with that. I mean, I've only really looked at things, dyes, like when they're late onto some kind of substrate. So I've only really seen them when they're functioning as a pigment in a pink layer. Yeah, well, we could talk later because I don't know exactly what your experience is, and I don't know if. Okay.
I was going to say the same thing. Sorry.
Hi, I'm Yvette. I'm a scientist at MoMA. I have a question related to the PCA. This might be really technical. Are there loading plots? What do the loading plots look like? Are you actually getting any kind of spectral information out of doing the principal component analysis? Or is it just, like, what is the underlying data? Because whenever I do PCA on something, I get loading plots, I get score plots, I get to interpret the data in relation to each other. And I was wondering if that's something that you get out of it.
Yes. In my particular case, I hadn't done a lot with that data yet. Really, this was sort of the first round. What can we pull out of this visually and give the conservators and the curators something interesting and quick to answer this very specific question? But yes, this is something that we need to dive into a little bit.
And I would say, usually when I'm doing like a principal component analysis, it's usually to try to improve visualization of something. So I'm not looking at loading plots. I'm looking at these like resultant principal component images. And I will say, those PC images, you can't really use them to identify materials. So you can have principal component images, and in one image, these different areas look white, for example, but that does not mean they're the same material, just so that's clear. Because in the next image, they might be two different colors, or they're all black. So I'm really just using it for like a visualization method, not really to identify materials.
I'm Deborah Mayer, and I have a million questions, but some are very general. When you say false color, is it any false color? Like, I make up my own channel, like I'll shift things to whatever channel I choose, and I was hesitant to call that false color because in the literature there's a prescription of what you change the channels to, and I'm not following that necessarily. And is that still in this world here called false color imaging? Do you use that terminology for any?
False color imaging for me is more mapping techniques, and there are certain published conventional approach. So false color IR, false color UV, you have to create certain substitution, channel substitution. But false color for me is actually can combine any three gray screen imaging into one. And the idea is to contrast the differences or reveal similarities. So that's basically, so that's in my video actually I show you actually you can just choose 3 bands and then just go through circulate to put into red, green, and blue channel or green, red, blue channel. And the idea is to get the most contrast image so you can kind of separate, like what Kay was doing, visualize the differences.
Okay. So it's 3D.
Yeah, I would say absolutely what you're doing is creating a false color image. So you can use any spectral band image you want and place it in the blue, green, and red channel. I would just advise you to label what spectral band images you're using. Because I think historically, like people call it a false color infrared image, where they replace the red channel with the infrared. And then they put the green into the blue and the red into the green.
You can get results. You don't follow that.
Yes, yeah. So I just say experiment with what you want. It's a false color image. I would just label what you do. Yeah.
So I do know there's some paper talking about using false color IR to identify different inks, and I usually caution for that because it depends on the lighting, depends on the camera, depends on how you process images. So the result may be slightly different from one to the other. And also it can be, it's better to have actually known sample to actually in the image together. So we actually can compare, and that will be the way I would identify material. But usually I generally don't use false color to identify particular material.
I would just add, I'm not usually using, you're usually only in a false color image, you only have 3 spectral bands. You get 3 data points. So it's really kind of hard to identify a lot of materials with just 3 data points. Usually I'm trying to look at like the spectra. You can definitely separate materials, but in terms of identification, I would really start looking at the spectra or more spectral bands.
And so for me, false color is giving me a map, so I can actually go to the particular point for more analysis. And so just getting a good map about what the differences are, and then go for the spectral analysis from there.
Hello, I'm Alexis. I'm a conservator at the Penn Museum. Actually, 2 unrelated questions, hopefully they're short. My first question is, it was kind of our understanding that we use a spectrum standard that it can degrade with UV exposure, and so you still recommend including a reflective standard like that in UV imaging. Do you have like advice? Like, is that just something that we could replace regularly, or is there something else that we could be using instead, or is that not actually true?
I don't know if it degrades. I'm not sure about that, but it is this. It's like a form of Teflon. It's sintered, but you can actually sand it, and maybe that would help. Like if the top layer does degrade. So I don't think you have to replace it all the time, but I definitely would suggest you still use it, just like to report on any light leakage in your system.
And I know the old one. Actually, I have the old set of the Spectral diffuse refraction center, and there are pigments. Actually, they don't have binders. It's pigments that are on the skin, and so the new one actually Teflon plastic, like the old one are pigments, and so they are, because they have no really binder in there, and so they're quite durable.
Thank you. My other question is, we work primarily with objects, so is there a point at which the dimensionality of what you're looking at can start to affect the accuracy of the data in these images of these cubes? As opposed to looking at something flat, like a painting or a paper.
3D objects can be challenging because your plane of focus is different. So you're going to be out of focus. So we've done things where, like in a multispectral system, you collect like a focus stack that can get around that. I've never done really hyperspectral reflective imaging on a 3D object, but kind of 2.5D, like a curved panel painting or something. But it is a challenge. I would just say you kind of want to look at the areas that are in focus, and then if you needed to do another collect, you'd be focusing at a different spectral depth and looking at your data.
Because for the reflectance imaging or to collect the data, I really need to have very even balanced lighting. Otherwise, the material response will be different because the lighting is not even. And so with the 3D object, it's challenging in terms of to get every facet have the even illumination to get the same, to get the balanced response. So 3D is hard.
Hi, great talk, guys. My name is Rachel, and I'm from Boston. So my question is about supply chain. I was wondering if you guys have any thoughts on any limited supplies. Like I'm thinking about multiband imaging, like the standard that we use for that. Some of the filters, we just ordered some PECA filters. It took about 8 to 9 months to get them in, but we did. So do you guys have any comments on if you guys foresee standards not being available anymore, or certain filters not being available anymore, or replacing filters with different ones? Do you guys have any thoughts on that specific for multiband imaging?
So for the upcoming Conservation 360, the chapter that I wrote is about tools and equipment. In there are a lot of tables about lights and filters, references, and there's also resources in terms of where you can get the camera modified. There's a lot of resources in that article. So keep an eye on that. In terms of the filter, it's also a challenge, and I did not present it. There are different filters and then called equivalent, but they are not really the same. So if you use equivalent, the information may be slightly different, so it can be consistent within your own studio, but may not be able to share with Others are using different filters, so that's something, a caveat to be aware about. Equivalent is not the same. And so I understand the PECA 19 is so hard to get by now, so I present actually using the X9BP1, very similar, it's equivalent, but not the same.
With the Conservation 360 upcoming volume that has been referenced, it is included in the reference list that was shared at the beginning and that will be on the online community. It's going to be a bilingual open access volume on multiband imaging that has foundational chapters that Jiuan was a contributor for, and then also case studies. So it will be a really phenomenal resource when it is available. It's still in process, and I think right now is in the translation stage. So keep an eye out. It will be available at some point.